Hi, I'm Brian Plancher, and today I'll be presenting accelerating robot dynamics gradients on the CPU, GPU, and FPGA. This is highly collaborative work done with Sabrina, Thomas, Scott, Srini, and Vijay. In this work, we show that by exposing different hardware-compatible features through refactoring and partitioning of our target algorithm, we can accelerate the gradient of rigid body dynamics on a GPU and FPGA by as much as 3 times end-to-end, including all I/O transfer overhead. But what I really want you to take away from this talk and from this paper is the notion that we should consider hardware-software co-design for parallelism for all of our robotics algorithms. That is, for all computational bottlenecks, we should consider refactoring our algorithms to expose more parallelism and to leverage parallel hardware architectures like GPUs and FPGAs in order to remove those bottlenecks and accelerate our robotics applications. In the rest of this talk, I'll first start with some motivation, then describe CPUs, GPUs, and FPGAs, our target algorithm, the gradient of rigid body dynamics, then I will describe our accelerated designs and our results. The gradient of rigid body dynamics is a key bottleneck for many planning and control approaches. For example, for nonlinear model predictive control, we find that computing the gradient of rigid body dynamics can account for 30 to 90% of the total computational time. At the same time, CPU hardware is not getting any faster. In fact, since about 2005, the clock speed of CPUs has remained relatively stagnant. This means that we need to find new ways to overcome these bottlenecks. We suggest that massive parallelism on GPUs and FPGAs can be one very effective way to overcome these limitations. Therefore, we need to consider how to best accelerate these algorithms on these more parallel hardware architectures. So let's talk a little bit about those hardware architectures and what are the real key differences between CPUs, GPUs, and FPGAs. First, your familiar CPU. It's got a lot of control logic, a pretty large cache, a couple of ALUs for some modest with vector operations. When you compare that to a GPU, what you'll notice is that a GPU trades off a lot of that control logic and cache memory for many more arithmetic and logic units. This means that GPUs are particularly well suited for operations that are naturally parallel and have very regular structure. So for example, if you think large matrix-matrix multiplication, the output for each cell is simply a row and a column being multiplied by each other. And this is the sort of regular data access pattern, standard sort of non-branching behavior that works quite well on GPUs. FPGAs, on the other hand, are a completely different kind of hardware. FPGAs have configurable logic blocks and interconnects, which allow you to compile custom chips directly onto the FPGA. So you can come up with your own little custom functional units that do a multiplication and a mux and a reorder, and then you can just stamp them out across the computational fabric. This allows you to mimic a custom chip, and actually FPGAs are usually used before a full ASIC is generally ever taped out to make sure to verify that that chip does work. Now, since these 3 pieces of hardware have very different properties, we find that in order to actually create software that can be efficient and effective and maximize these hardware capabilities, we need to do hardware-software co-design to refactor our algorithms to take advantage of the specific hardware features. On CPUs, we leverage the fact that they're very general purpose and easy to program using lots of different libraries that other people have optimized. On GPUs, we have some of that library support, but we need to actually refactor our algorithm for massive large-scale parallelism, as GPUs are not as fast on serial operation. FPGAs, on the other hand, are the fastest and still exhibit a decent amount of parallelism by having those custom functional units that we can stamp out across the fabric. Of course, we need to spend a lot of time to carefully design those custom functional units, and therefore they're the hardest to program. Now, before we can actually dive into our accelerated designs, we need to understand the algorithm that we're going to refactor and redesign for these different hardware platforms. And that algorithm is the gradient of forward dynamics for a rigid body robot. That algorithm can be broken down into 3 steps. First, computing some intermediate terms using the recursive Newton-Euler algorithm, then computing the gradient of the recursive Newton-Euler algorithm, and finally taking that gradient output and multiplying it by the inverse of the mass matrix to get the final result. Now, as you can see on the graph, the most time-consuming step here is computing the gradient of the recursive Newton-Euler algorithm, and for the rest of this talk, I'm just going to focus down on that step, although all of the features, all of the refactoring, and all of the optimizations we do are actually applicable to all 3 steps, and we do it to all 3 steps, but just for time, I'm just going to focus down on that one step. When we look at this algorithm, we can see a lot of different things going on here, and I'm going to walk through some of the key features. The first 2 features I want to discuss are fine-grained parallelism and a small working set. Now, these go hand in hand because a lot of these matrices and vectors that you see represented by variables here are 6x6 or 6x1 matrices and vectors. Therefore, the amount of memory we need to keep in our cache is actually quite small. That's that small working set. And we can have lots of fine-grained parallelism in those 6x6 or 6x1 matrix vector operations. The next feature I want to point out is the structured sparsity in this algorithm, as many of these terms are defined at compile time by the robot topology. So for example, if you have a z-axis revolute joint, the SI vector becomes just 0, 0, 1, 0, 0, 0. Therefore, instead of actually computing whatever term is multiplied by it, we can instead just compute and extract the particular row or column that we need based on the matrix vector multiplication or cross product operation. And that can save a lot of compute time and actually reduce our memory requirements as well. It is also important to note that this algorithm has a lot of irregular memory access patterns and a lot of sequential dependencies. This is important because this limits the natural parallelism in the algorithm. The sequential dependencies come from the lambda i's, which refer to the parent link of each of these joints, and therefore these loops cannot actually just be unrolled in parallel and instead have dependencies between them. The irregular memory access patterns come from the fact that the cross-product operations are a reordering and then a matrix vector multiplication. Finally, when we consider this algorithm embedded inside the context of nonlinear model predictive control, we find that it's not important to just compute one dynamics gradient evaluation, but instead we need n evaluations for the n knot points along that trajectory, and this creates natural coarse-grained parallelism. Also, when using GPUs or FPGAs, we need to consider the I/O overhead of sending memory to the accelerator and back once we've computed the solution. So now that we know the high-level algorithmic features and structure of the algorithm, let's consider how we use this to influence our designs. I'll talk about the CPU, GPU, and FPGA designs in brief here, but defer to the paper for a more detailed discussion. With regards to the CPU, we find that the CPU is actually relatively well suited for many of these algorithmic features outside of that large-scale parallelism, as most CPUs only have 4 or 8 cores instead of the n we would need for all the points along the trajectory. Therefore, we can pretty much just simply implement the algorithm as is and leverage existing libraries like the eigen library for efficient fine-grained parallelism on the matrix math. On the GPU, on the other hand, we find that it's actually quite not well suited for many of the features in this algorithm. Those irregular memory access patterns and sequential dependencies really break a lot of the large-scale parallelism with which the GPU thrives. Therefore, we have to find new ways to refactor the algorithm to expose more parallelism, allowing us to take advantage of its really good coarse-grained and fine-grained parallelism. Therefore, what we do is we refactor the algorithm to expose a lot of temporary variables. So we create a lot of these temporary variables in fully parallel loops, doing one kind of operation at a time. So matrix vector multiplications, then cross products, then some more matrix vector multiplications, etc. By doing these unified steps with lots of parallelism, we can actually take advantage of the parallelism available on the GPU and do it in an efficient way that doesn't require as many synchronizations. Therefore, in those loops that do require the synchronizations, we can do as little work as possible to as quickly as possible get through those loops. The FPGA, on the other hand, is actually quite good at a lot of these irregular access patterns with small working sets, as we can create these custom functional units that can just directly encode these sorts of operations. Right? We can do a mux into a multiplication tree that makes sure we pull the right things from one vector and from another to quickly do a cross product really super rapidly. Now, the one downside here is that the gradient of rigid body dynamics is a relatively complex algorithm that involves a lot of custom functional units, and therefore it takes up a lot of space. And what we found was that in our implementation, although in theory we could stamp out many gradients at the same time across an FPGA or an ASIC, in practice, with a very, very large FPGA which we had, we could actually only fit one gradient at a time, basically removing any sort of coarse-grained parallelism. So, once we did all these optimizations, we can then look at our results, and we can consider how well these things can be accelerated, and how well these sorts of refactorings can actually improve upon the state of the art. And so we chose an Kuka-Iwa arm as our example robot. I want to point out that this is actually probably the worst choice from a parallelism perspective. As you can imagine on a quadruped or a biped, you may be able to compute links in parallel. Here we just have one serial chain manipulator, and so these results are sort of hindering our GPU and FPGA results, and yet we still find gains. And I think this sort of just shows how important it is to consider this sort of hardware acceleration through parallelism in future robotics work. Anyway, diving into the results, we see that by putting in some of these optimizations, like taking advantage of the structured sparsity, our CPU implementation is able to outperform the state-of-the-art by 1.5x. And we'll compare our accelerated GPU and FPGA implementations to this new accelerated CPU baseline. We find that the GPU is actually not good at computing an individual gradient at once. And this makes sense, right? Because the GPU's biggest strength is that coarse-grained parallelism, and when we're only computing one gradient, we can't really take advantage of that. That said, this refactoring greatly improves on the state-of-the-art with a more than 6x increase in speed over what exists out there, and brings the compute time for a single gradient evaluation more in line with the CPU. On the FPGA, on the other hand, we see that computing all these custom functional units leads to a tremendous speed up with a more than 5x increase over the CPU, over our optimized CPU implementation. That said, what's important in the context of nonlinear MPC, and where we can really see the GPU shine, is when we need to compute n computations in parallel for, say, n knot points along a trajectory. And here, we see that both the FPGA and the GPU both outperform the CPU across n equals 16 to n equals 128 computations. And this is because the FPGA is just straight up faster. And even though we weren't able to stamp out many gradient evaluations at a time, each evaluation is so fast that it outperforms the CPU, even when the CPU is using quad-core parallelism. And at the same time, the GPU is able to get up to a 3x speedup at 128 knot points by taking advantage of its large-scale parallelism. And you can really see how the GPU results just scale the best. And that makes sense, as we're taking advantage of its ability to do parallelism well. I also want to point out that one of the largest drivers of time for the GPU and FPGA is that I/O overhead. And so this suggests that if we can move the whole nonlinear model predictive control algorithm onto the GPU, or onto the FPGA, we can start to eliminate a lot of this I/O overhead and get an even increased speed over the CPU. In fact, in the case of n equals 128, the I/O is more than half of the time for the GPU. So what's next? Well, I want to point out two things. One, as we said, our FPGA was hindered by the fact that we basically filled up the whole FPGA with one computation. And so in our sister paper, Robomorphic Computing, which was presented at this year's ASPLOS conference, we started down the path of considering ASIC synthesis and building a custom chip. Here we found that actually simply moving from an FPGA to an ASIC can give us a 4 to 7x speed up in time over our already very fast FPGA implementation for one gradient evaluation, and would allow us to stamp out many gradient evaluations onto our own custom chip as we continue down that path. The other thing I want to point out is probably one of your biggest questions is, okay, that's great, you did this for the KUKA EWA arm, how do I do this for my own robot? And I'm excited to tell you that we're currently working on a new code generation approach that will allow you to give a URDF to our system, and it will spit out optimized GPU or FPGA gradient code for you to use in your own application. So look for some exciting results coming out for that in the coming months. In the meantime, if you'd like to check out our current CPU and GPU results, you can find that on GitHub by going to bit.ly/fast-rbd-grad. So in conclusion, hardware-software co-design for parallelism can be very powerful, but it does require fundamentally understanding the hardware that you're targeting and your algorithm to make sure that you can refactor it and partition it to make sure that it is implemented as efficiently as possible on your target hardware. Thank you, and I hope you enjoyed the presentation.